the solutions for this. We have a substance that's found to be 5.34% beryllium and 94.66% bromine. What's its empirical formula? Because these are given as percent data, this is where you have to do the magical 100-gram sample. So in 100 grams, you'd have 5.34 grams of beryllium, and there are 9.01 grams of beryllium in 1 mole of beryllium. On a few of your papers, I wrote label better. I know it seems crazy, but putting in that this is grams of beryllium and this is grams of beryllium and this is moles of beryllium really helps you, because right now we're doing factor labels where everything is one chemical, but in chapter 9 we'll be doing factor labels where you're dealing with multiple chemicals and multiple units. So when I say units and chemical, I mean it. And also, you know, in a few cases there were little tiny tracking errors that cost you the question just because you kind of forgot which thing went where. So doing that really helps. So we get 0.5926, etc. moles of beryllium. And then we look at our bromine. And notice that I even put the beryllium there because that helps you. So then we have 94.66 grams of beryllium, 79.90 bromine, geez Louise, in 1 mole of bromine. And that gives us 1.18473, etc. moles of bromine. Okay, so we're going to take the smaller of those two numbers, divide each of them by it, and that would be our moles of beryllium. Obviously, let me shrink this. We get a 1 there, we get a 2 here. The reason why having those labels in there helps you is because you don't mix up your subscripts. So we have beryllium with the subscript from this whole line being about beryllium is 1, and bromine with a subscript, and this whole line of course is about bromine, so that's 2. So it's BeBr2, beryllium bromide, ionic compound. And the if you think about it in terms of does this line up with what you know about how an ionic compound forms? Yeah, beryllium would typically have a 2+ charge, bromine has a 1- charge. It lines up. When the compound is something that's ionic, you can kind of do that as a double check. And how many of you are starting to find yourselves doing that sort of subconsciously? Like, oh, does that make sense as a compound? Yeah, okay. That's a good thing, because it means that you're becoming literate in chemistry. You're actually seeing a larger pattern. It's like the difference between the kind of reading a first grader does, where they're picking out individual words, and the kind of reading you do, where there's a flow of information. So that's really good if you're finding yourself doing that. Okay, in the next problem, you're actually given the composition information in mass, so you don't have to make that magical 100-gram sample. And we're told you have 1.396 grams of iron and 1.05 grams of nitrogen, and should have been 3.6, not 36, my apologies, 3.60 grams of oxygen. So we put in our molar masses, and I'm going to shortcut this a little bit. I did all the detail. Now I am physically incapable of shortcutting it, aren't I? So I put in all the detail on the key. So we're going to do all that. We get 0.024995, etc. moles of iron. Here I'll shortcut it. We get 0.07496 blah 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 moles of nitrogen, and we should get 0.225 moles of oxygen. So we're going to divide each of these by the smallest of them. There, I'll do that. And so, of course, we get a 1 for our subscript on iron. I'm going to divide each of these. So that's a 1. That's a 3, and that's a 9. So we've got, iron with a subscript of 1, nitrogen with a subscript of 3, and oxygen with a subscript of 9. You got full credit for writing the empirical formula if you wrote that. But what a lot of you noticed, and what I was really happy to see, is you went, oh, that looks like iron nitrate. And you said to yourself, I think that's actually FeNO3 3 times. Because you had to write the name too. And many of you knew, well, this is iron, it's going to have to be stock system, it's going to have the parentheses with the which iron ion we're talking about. Well, once you remember that this is NO3 3 times, then you go pretty easily, oh, it's iron 3 nitrate. So that was the correct answer for that. Iron 3 nitrate. And if you said just iron nitrate, I took off a half, I think. Okay. Number 3 was pretty easy if you didn't overthink it, which we're prone to do, especially once we've added a lot more complex skills on top of the simpler skills and we've mixed them all up. So, compound with empirical formula of CH2 has a molecular molar mass of 28.062 AMUs. What's its molecular formula? Here's what you have to remember. Molecular formula mass divided by empirical formula mass gives you your multiplier, and that's what's going to tell you what you need to multiply the subscripts by. So it's pretty easy to add up the empirical formula mass for this one. We get 14.03. So we're just taking 28.062 AMUs divided by 14.03 AMUs, and of course we get a multiplier of 2. It's 2.000 something. Close enough to 2, we assume that the rest of it is just a rounding issue. So what we end up with is C2H4 for our molecular formula. And most people did pretty well on that one. Okay, the last one is where you have to put everything together start to finish. Okay, so finally got smart. There's a picture of darn key. And right on top of it saves us a lot of time. So here again, you're given the composition as a percentage, so you have to do the 100-gram sample. You're finding out how many moles of each you have, and this level of good labeling, where you're putting in units and chemical, is really important because that's what helps you keep it straight. It's a bookkeeping thing. When we get into the stoichiometry in Chapter 9, that bookkeeping becomes essential. And if you're going on to take physics, that bookkeeping is huge in terms of success in physics. So we get those, we divide out our ratios, we get 1.99986, etc., and 1.99. So we have an empirical formula of KCO2. And I looked at that and I went, potassium carbonate, but that'd be K2CO3. Whoa, 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 whoa. Trust the calculations. So that was like, I leapt to that. I thought, oh, this can't be right. No, 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 no. Back off, trust the calculations. Remember that that's just the empirical formula. So we were told that there is a molecular or formula mass of 166.22. So we have to get the empirical formula mass from this, and sure enough, it's 83.11. This is not the empirical formula, or this is not the molecular formula or formula. We get a multiplier of 2 when we go through our process. which means we have K2C2O4. What would that compound be called? I didn't ask you this, but it's a good question. It's potassium something. Oxalate. Yeah, it's potassium oxalate. And that's a compound that's commonly found in things like chard and spinach and other dark leafy green vegetables. People who are prone to kidney stones are told to avoid those things because kidney stones are actually oxalate crystals. And so people who are prone to kidney stones who eat lots and lots and lots of things that contain potassium oxalate are predisposed to forming kidney stones. So anyway. Questions, comments, or concerns on the quiz? You guys did really well overall. I'm really, really proud of you. Yes, ma'am.
Do you not have to put it in the percents? Just leave it
This one?
Yeah.
Yeah, you don't. If it's given to you in mass, you don't have to change it to percents. Because if you think about it, if it's given to you in percents, you're changing it into mass because you want to get the number of moles because you're looking for mole ratios. You don't have to do that extra step. You've already got masses.
Would it make a difference if you
I don't know.
No.
It's just you're just adding work. No, and you got it right.
Yeah.
Yeah, you're adding a step for yourself, but it doesn't matter.
Okay.
So yeah, you can go ahead and find the percent comp of each, and then make a 100 grand sample. It just takes you time. So yep. Other questions? Okay, wunderbar. You got time to work.